Hello seniors, today we're going to continue with electronic assignment number 16, extrema and optimization problems. This is part 3 of the video. And today we're going to see optimization, which is a very important concept because it is widely used in our daily lives, right? In order to maximize profit or to minimize costs or maximize a possible area or whatever, we apply the concept of optimization, okay? So let's see, it says many practical problems involve finding maximum or minimum values. For example, we may want to maximize an area or minimize cost. Such problems are called optimization problems. So here's a step-by-step process in order to find optimized values, okay? And we're going to see all of these 4 steps through different examples. It says for optimization problems, number 1, assign variables to given quantities and quantities to be determined. When possible, draw a sketch. This is very important for some problems. Number 2, write an equation to be optimized, either minimized or maximized, in terms of 2 variables. Number 3, find values that are sensible or feasible for the problem situation where the derivative of the equation to be optimized equals 0. Finally, number 4, verify that you have a minimum or maximum using the first or second derivative test. If the domain is such that x is in between a and b, 2 values a and b, remember that the endpoints must be tested since the maximum or minimum on a closed interval can occur when f prime equals 0 or also at an endpoint. This is according to what we have seen in last class, right? We can have an absolute maximum or minimum in an endpoint and not necessarily where the first derivative is equal to 0. So it's important to verify that. Okay, so let's see some examples in order to visualize how this concept of optimization works. It says, the product of 2 positive numbers is 48. Find the 2 numbers so that the sum of the first number plus 3 times the second number is a minimum. Okay, so for every optimization problem, we have, first of all, an objective. In this case, the objective is to minimize the sum of the first number plus 3 times the second number. Okay, that's our objective. And for every problem, we will have a constraint. A constraint means a condition that needs to be fulfilled in our problem. In this case, the condition or constraint is that the product of the 2 positive numbers must be equal to 48. Okay, so if I call, for example, the 2 numbers x and y, right? We're going to say that in order to write the constraint into an equation, we're going to say that x times y should be equal to 48, okay? So this is what we know as the constraint of the problem. Constraint. Every optimization problem will have a constraint. So from this constraint, what I'm going to do is I'm going to solve for one of the variables. That means leave one of the variables alone. For example, y, I could leave it alone and say that this is 48 divided by x. Okay. Then I will focus on my objective. My objective is to minimize the sum of the first number, which is x, plus 3 times the second number, which is y. So if I write this into an equation, I'm going to say that x plus 3y must be a minimum, right? I want to minimize this sum. So from my objective and also from my constraint, I see that, for example, what I can do is I can plug in this, which is y, into my objective, right? Instead of writing y, I'm going to write its equivalent, which is 48 divided by x, which comes from the constraint, right? So I can say that this is x plus 3 times 48 over x. And we want to minimize this, right? I'm just going to write min, right, for minimum. Okay, so once I have done this, well, I can work with this a little bit. X plus 3 times 48, that's 144 divided by x. And this would give us a minimum, right? Min. Okay, so What I need to do next in order to minimize this is to find the minimum point of this equation over here, right? And to find the minimum point of a function, I need to apply the concept of derivative, right? I need to find the derivative of this function and set that derivative to 0 in order to find a critical number that would represent either a minimum or maximum point. We need to check that, right? So since we need to differentiate this, I'm going to rewrite this expression first as x plus 144 times x to the power of -1. If I take this up here, in order to be able to find the derivative, then that's x to the power of -1, right? And this is our minimum function, the function that we want to minimize. Okay, so let me write here what I just said. To find the minimum, we calculate f prime of x, the derivative of the function, and set it to 0. Set it to 0. So we need to find f prime of x and set this to 0. So that's exactly what we need to do. So I'm going to differentiate this expression. Maybe if I rewrite this as f of x equals x plus 144x to the power of -1. This is more familiar to you, right? So now I'm going to find the derivative, f prime of x. And to find the derivative, we already know the derivative of x is equal to 1. And the derivative of x to the power of -1, the -1 comes down to the front, so we get minus 144 times x to the power of -2, right? So if I rewrite this, we're going to say that f prime of x is 1 minus 144 over x squared. But now we need to set this to 0. So we're going to set this to 0 to find either maximum or minimum point. So 0 is equal to 1 minus 144 over x squared. And now I need to solve for x, right? I can say that this is equal to 144 over x squared. Then I can take the x squared multiplying up. So we're going to get that x squared is equal to 144. So if I take the square root of both sides, square root of x squared equals the square root of 144, we're going to get as an answer, remember square root has two solutions, so plus or minus 12, right? Square root of 144 is 12. So there are two possibilities. Either x is equal to positive 12 or x may be equal to negative 12, right? So if we look at the problem says the product of two positive numbers, okay? So with this information, two positive numbers, we can discard the negative 12, right? This is not valid. Not valid because it is a negative number, right? Negative number. Okay, so our solution for the x value is 12. But now that we have the value of x, which is 12, we still need to find the value of y. We know that y is calculated this way, 48 divided by x. So y, let me write it here, y is equal to 48 divided by 12, and 48 divided by 12, that's 4, right? 48 divided by 12, that's 4. Okay, so there we get the two results. X is equal to 12, and y is equal to 4. Those are our solutions that are supposed to be the solutions that give me a minimum sum between the first number and 3 times the second number. Let's do an experiment in order to see if this is true. Okay, so we're gonna try this. Let's try this. Okay, so we're gonna write a value of x, a value of y, and we're going to calculate what the problem is saying. The problem is saying the sum of the first number plus 3 times the second number. That's the condition of the problem. Okay, so if we do this, let me separate this. like this, we know that the product must always be equal to 48 according to the problem, okay? So we're going to think about all of the pairs of values which give us as product 48. So for example, the first product is 1 and 48. If x is 1 and y is 48, the product is 48, right? And if we do x plus 3y, we're going to get as a result 1 plus 3 times 48. 3 times 48 is 144, plus 1 is 145. So this is what we get as a sum, right? Then another pair of values would be, for example, 2 and 24, right? If we apply the formula, we're going to get as a result 74. Then another pair of values would be 3 and 16. If we apply this to the formula, we get 51. Then 4, 12 is another pair of values. This would give us 40. Then 6 and 8 is also a pair of values. This gives us 30. 8. Now I need to do the same thing, but in the opposite way, right? Now I'm going to say that x is 48 and y is 1, for example. So I'm going to switch the values in order to contemplate all of the different possibilities, right? So here, 8 and 6, for example, this would give us 26. I don't know if I will have enough space. Maybe if I take this a little bit down. Oh. I'm going to take this up a little bit. There. This is to the power of -1. Okay, so I have a little bit more space there. So then we have 8, 6, then 12 and 4, which is our solution, right? 12 and 4. If we apply this to the formula, we get as a result 24. Then 16 and 3. 16 and 3, this produces 25. Then 24 and 2, this produces 30. And finally, our last option is 48 and 1. And this produces, as a result, 51, if we apply it to the formula. Okay, so you can see, as you can see, there, as you can see, the result that gives us a minimum for x plus 3y is actually this result over here, right? Which is exactly the result we obtained by doing our optimization method, right? X is equal to 12 and y is equal to 4. There is no other possibility that would produce a smaller number than this 24 over here, with the constraint that the product of the two numbers must be equal to 48, okay? So there you have. This is an example of how optimization works, okay? Let's see another example to visualize this better. This is a more practical, real-life example. It says, a rectangular plot of farmland is enclosed by 180 meters of fencing material on 3 sides. The fourth side of the plot is bordered by a stone wall, so there's no need to put fence in that wall. Find the dimensions of the plot that enclose the maximum area. Find the maximum area. Okay, so if we do a sketch of the situation, in this particular problem, it's better if you do a sketch first of all. So let's make the stone wall first, right? Right here we would have a, let's say a stone wall. So there's no need to put fence in this particular wall. And then for this side, this is a rectangular plot, right? So we need to do a rectangle, something like this. On the 3 sides, colored in red, we're gonna have fence, right? So I can call this, for example, X. The length would be Y because it's different, and this width would be X because it's the same as the other one. Okay, so it says, a rectangular plot of farmland is enclosed with 180 meters of fencing material. So this data, in this case, would be our constraint, right? We only have 180 meters of fencing material. We cannot use more than that because we don't have that. But if we want, we can use less than that. But I don't know if it is convenient to use less if we want to maximize our area, right? So that's our constraint. We only have 180 meters of fence. So if we write this constraint, what is this constraint about? It's the perimeter of this rectangle, but excluding this wall over here, right? Because for that wall, we're not fencing. We're not fencing the wall, right? So our constraint would be that 180, the whole fence, should be equal to 2x plus y, right? 2x plus y is all of this. So that's our constraint. Let's write here. Constraint. There you go. So my objective, let's write the objective. The objective is to, in this case, maximize area, right? So maximize the area of this farmland. So I need to determine the dimensions of x and y that will maximize this area. Okay, now that I have my constraint and my objective, I need to write this objective into a mathematical equation, right? So how do we find the area of a rectangle? It's easy, right? It's x times y in this case. So the area, which I want to maximize, is x times y. X times y. So I have the objective and the constraint ready. So from the constraint, I'm going to leave one of the variables alone, right? In this case, it's easier to leave the y alone because it doesn't have any coefficient in front. Well, the coefficient is 1. So I will say that y is equal to 180 minus 2x, right? From the constraint. And this, we're going to substitute into the area equation, into the objective equation, which in this case is an area equation. So the area, I'm going to do it here. The area is x times, and instead of y, we're going to write this equivalent expression, right? Times 120 minus 2x. Okay, so there we have. Our objective formula, or our objective equation, is now written in terms of only one variable, which in this case is x, okay? So if I work with this equation, we're going to say that area is equal to 180x, if I distribute the x, minus 2x squared, okay? So if I want to optimize something, either minimize or maximize, I know that I need to differentiate this equation. I need to find the derivative of this expression. So I'm going to say that this is a prime. The derivative of the area is, and in this case, it's 180 minus 4x. Okay? So let me write that down. If I want to optimize, I need to set the first derivative to 0. Okay, so once I do this, I'm going to set this to 0, and I'm going to find the value of x, right? So this would be 4x is equal to 180. So the value of x would be 180 divided by 4, and that is exactly 45. In this case, we're talking about meters, right? So 45 meters. Okay, so we have a possible value of x. We need to see if this minimizes or maximizes the equation. With this value of x, I can find the value of y, right? Which is found by replacing the value of x into the constraint, right? Y is equal to 180 minus 2 times 45. 2 times 45 is 90, so 180 minus 90, that's 90 meters. Okay? Now, how do I prove if these two values I obtained are actually maximizing or minimizing the equation? Well, we already know how to do that. If we want to determine whether these two values correspond to a maximum or a minimum, I can try doing the second derivative test, which is the one that we learned last class, right? If I find the second derivative of this expression, the second derivative of this would be a 0 minus 4, right? Minus 4, and this is a negative number. And if it's a negative number, then the values x equals 45 meters and y equals 90 meters both correspond to a maximum point. Remember, when the concavity was negative, it means that the function is bending downwards. So that means that this point over here must be a maximum, right? So with this information, we conclude that these 2 points are actually producing, or these 2 values are actually producing a maximum point. Okay, so already it says find the dimensions of the plot that encloses the maximum area. So these are the dimensions. X should be 45, this should be 45, and this should be 90, right? And then it says find the maximum area. How do we calculate the area? We just need to do x times y. So the area is equal to x times y, which is 45 times 90, and 45 times 90 is equal to 4,050 meters squared. Okay, so this is the maximum area, and these are the dimensions of our rectangle, of the rectangle that will maximize the area. And if you want to make an experiment, you can try finding different pairs of values for x and y, and you will see that none of them will produce an area which will be greater than 4,050. Remember that the constraint should always be fulfilled, right? So if, for example, if you're gonna try, let's do an experiment. If we say that, for example, x is equal to, let's say, 50, then y should be equal to, this is 50, 100, so we only have 80 meters left, so y is equal to 80. If I calculate this area, 50 times 80, this gives us 4,000. And 4,000 is a value that is less than 4,050, okay? So you can try this with any pairs of value as long as you respect the constraint, and you will see that it is impossible to get a value that is greater than 4,050 as we got in this problem. You can try that on your own if you want. Okay, so let's see another example. This one, example 31. It says find the dimensions of an open box with a square base and a surface area of 192 square meters that has a maximum volume. Okay, so in this case, our objective is to maximize volume. And our constraint is that the surface area must be 192 square meters. Okay, that is our constraint. And one other detail you need to pay attention to, it says an open box. If it says an open box, it means that it has all its faces except the one on top, okay? So the first thing I always recommend to do in case you can do a sketch is to actually do the sketch, okay? So we're gonna start by doing the sketch of this situation. We need to make a box. This is a square base, right? So it will look something like a cube. Let's see, something like this, like that. Oh, there's something wrong here. This is 4, there. Okay, so we do the box. We know that it is an open box, right? If it is an open box, that means that we're not considering, let me see if I can show this maybe in gray. All of this interior part, or all of this top, doesn't exist, okay? It's just, it's free space up here. There's no face here. Okay, so once we have done the sketch, we need to name our variables. If this is a square base, it means that the length is equal to the width, right? But the height could be a value different from x, so we're going to call this y, okay? This is also a height. Okay, so that's all the information we have. Then we're going to use the constraint. We know that the surface area, is equal to 192 centimeters squared. How do we calculate that surface area? Remember that the surface area of a 3D shape is the addition of all of the areas of all of the faces, right? So we need to add the areas of all of the faces, basically. So how do we do that? We know that the bottom base is x squared, right? X times x. And then we have 4 faces, which the area is equal to x times y, right? X times y. So basically the surface area, which is 192, is equal to x squared, which is the bottom area, plus 4 times x times y, right? Which are the lateral areas of this particular box. Okay, let me fix this 4, which is a little bit ugly. There. Okay, so this is our constraint. Let me write here, constraint. Now, from our constraint, we need to, as always, try to leave one variable alone, right? I see that the y is easier to solve. It's easier to leave alone than the x. So that's exactly what we're going to do. We're going to leave the y alone, okay? So we can say that, for example, 192 minus x squared is equal to 4xy. So if I take all of this 4x dividing to the other side, we're going to get that 192 minus x squared. All of this is being divided by 4x, and this is equal to y. Okay, so there we have our constraint, which is in terms of x already. Now, our objective, let me write this here, objective is to maximize volume, right? So maximize volume in this case, volume. Okay, so once we have written our objective, we need to write this into a mathematical expression, right? How do we calculate the volume of a box, of this box? The volume, remember the formula for volume? It's area of the base times the height of the box, okay? So area of the base times height of the box. If we write this in terms of our letters in the problem, the area of the base is x squared, right? So x times x, which is x squared, and the height is y. So x squared times y. This is the expression of the volume. But from the constraint, we have already written y in terms of x. So we're going to replace all of this, which is y, all of this, here, instead of y, right? So the volume is equal to x squared times all of that, 182 minus x squared divided by 4x. Okay, so we need to organize terms first before we start doing the derivatives. So we're going to say that the volume is equal to, if we multiply this, we're going to get 192 divided by, before actually multiplying, see that this x simplifies with this one over here. So 192 divided by 4, that's 48. 48 times x, that's 48x. And then x times x squared, that's x cubed. And this is divided by 4. Remember, this 4 divides both of these terms. Okay, so I think we can get up to there for the expression. X cubed, yes. So now that we have our expression simplified in its simplest form, we need to find the derivative of this in order to find the optimal value. So we're gonna find the derivative of this expression, and this would be 48 minus, this is 3x squared over 4, right? 3x squared over 4. So we have found the derivative, and we need to now set the first derivative to 0 in order to find critical numbers. So 0 is equal to 48 minus 3x squared over 4. And then we need to solve for x. If we solve for x, I'm going to do it here. This is 3/4 of x squared, and this is equal to 48, right? Maybe if I take this a little bit down to make it fit. There. Okay, so if I take the 4 multiplying here and the 3 dividing here, we're going to get that x squared is equal to 64. 48, yes, 64. So if we take the square root from both sides, x squared square root of 64, the square root of 64 is plus or minus 8, right? So there are two possible values for x. Either x is equal to positive 8 or x is equal to negative 8. Negative 8. Remember that in this problem, we're talking about, first of all, centimeters. So if we write unit of measurement, this is centimeters. And then we need to analyze the result. Can we have a negative length for the box? No, right? So we can, in this case, automatically eliminate this because we cannot have a negative length, right? So we only stay with this value, which is x equals 8. So once we have this value that corresponds to x, we can find the value of y, right? So let me do that right here. If we find the value of y, we're going to say that y is equal to, and we need to bring all of this down, right? It's equal to 192. I'm going to put this a little bit up. This is 192 minus 8 squared divided by 4 times 8. 4 times 8, this was our constraint, yes. If we do this, if we perform this, we should get a value of y, which is 4 centimeters. But before stating that this is the final result, we still need to prove that this pair of values, 8 and 4, actually correspond to a maximum, because we want to maximize volume. So that's exactly what we're going to do. We're going to prove that. In order to prove that, I first need to find the second derivative. So I'm going to take the first derivative here, and we're going to find the second derivative of this expression, which would be a derivative of 48, that's 0, and the derivative of this would be 3x over 2, right? Because the 2 simplifies with the 4. So, I forgot the negative sign. There. Negative 3x over 2. That's the second derivative, right? Now, if I try the second derivative for this value of x, which is a critical number, if I try that number into the second derivative, I'm going to find the second derivative evaluated for x equals 8. This would be negative 3 times 8 divided by 2. Negative 3 times 8, that's negative 24, divided by 2, that's negative 12. So we see that we get a negative number. And as we get a negative number, we can conclude that x equals 8 is actually corresponds to a maximum, right? So with this result, we confirm that x equals 8 and y equals 4 is actually producing a maximum volume, which was our objective for this problem, okay? So let me write the final answer here. We're going to say that x equals 8 centimeters, y equals 4 centimeters, are the dimensions that maximize volume. Okay, we have one exercise pending, but in order to not make this video too long, I'm going to leave the video right here, and we're going to be solving that last example together in a future live session. Okay, so I hope that was clear for you seniors. If not, please let me know. We're going to clear it out in future live sessions. Thank you for your attention. See you.